Hello everyone and welcome back. In this video, which is the second one out of 3 in the series, as I promised, I'm going to be showing you how to apply what we learned in video 1 into actually solving integrals of products of sines and cosines. So in the table that I have here, I've absorbed all of the important results from the video that you should have just watched, part 1. And they're all laid out for you in order to know what's important and what you need to know. Now, provided you know this stuff, we are able to just jump straight in and you will see how seamless this knowledge makes solving the integrals at hand. So let's start over here with an example where the actual power of sine and cosine in the product is odd for both of the trig functions. What are you supposed to do here? Well, one thought that we want to have in our mind is that we're chasing to make this into one of the formats that we have in yellow over here. So which one is more likely to work? Well, I see again over here that sine, and it has a cubed power. Now, if I was to make use of the Pythagorean identity, which again is this guy over here, if I was to make use of that, I could drop 2 powers of that sine, leaving me with a single sine. And that would mean aiming for the format of, again, cosine to the n power, sine x dx. So I would be aiming for that format right there. Now, again over here, if I do that, let's see what happens. If I break down that sine, I start by using the Pythagorean identity here, drop 2 terms of the sine, leaving me with a single term, and then having the cosine to the 5th here completely untouched. Now I can distribute over here my result, and I should get cosine to the 5th x, sine x, and that's one integral, and then break the other integral as cosine to the 7th x, and then sine x dx. Now, quite obviously, this is again falling under the category right there. And we can integrate because we know the pattern. We've discussed it already. Don't forget to flip the results signs. So let's go ahead and do that. We gotta raise the power of that cosine by 1 and divide by that new power. So we have cosine to the 6 over 6 and then cosine to the 7 over 7. The sign here is positive, so it's going to be negative in the result, and the sign here is negative, so it's going to be positive in the result. Merge them together, and don't forget your integration constant, c. And that basically sums it all up. You can see how much simpler this is becoming. So another example I've laid out, I'm going to try all combos here of exponents. Another example I have is switching here the sign to have an even power, and the cosine to have an odd power. So once more, it seems like the cosine is the easier function to be broken down using the Pythagorean identity, and it will leave me a single factor of cosine to be carried along. So I will go ahead and abuse that. I'll have my sine here untouched, and then drop 2 powers of cosine by writing them like this. And then I'm going to remain with 1 power of cosine, and that's it. Now I'm going to go ahead and distribute, getting myself here sine to the 4th x, cosine x, and then I'm going to go ahead and have sine, let's not forget the dx, and then I'm going to go ahead and have negative sine to the 6th x, cosx dx. So if I integrate this, this is falling now under the category of the sine function up there. So you can see how I will integrate it. Basically boost the powers of sine by 1. So sine to the 5th and sine to the 7th here. And divide by those new powers. So divided by 5 here and divide by 7 there. Keep the signs the same as they were before. So we're going to have a negative for the second integral. Merge them together and don't forget your integration constant. And that's it. Really, it is that simple once you know what we've already learned. So, the third integral over here that I want us to take a look at is, again, similar, where now I have an odd power for sine and an even power for cosine. Once again, it seems like I should go this direction and break this sign down because I can remain with a single power of sine, which is one of the formats I have that I know how to solve. And I go ahead and do that by introducing again the Pythagorean identity, replacing two factors of sine. I remain with one factor of sine and the cosine squared untouched. And then I go ahead and distribute over here, so I get cosine squared sine of x dx, and then I remove over here, I take away cosine to the fourth x, and then sine x dx. So how do you solve these again? They fall into the cosine pattern, where we have to again raise the power of those cosines by 1. So we have cosine cubed and cosine to the fifth here. We're going to divide by those new powers, and we can't forget to actually flip the sign. So that one here is going to be a negative, and that one here is going to be a positive. We merge the result together, and we don't forget about our integration constant. And that's the story. Really, it is that simple. So one more case that you could have, getting a little bit more convoluted, is what if the powers, again, were both even, let's say, and you have something like this. So this one is a little bit different, but again, it's nothing that you can't deal with what you already have at your disposal. But I just want to show you that regarding the choices you can make here, you might get a longer approach or a shorter approach. The longer approach that I'm not going to do is you might be tempted to kill this sine squared in favor right now of 1 minus cosine squared, and then leave that cosine squared alone. If you distribute, I hope you see, get the integral of cosine and then the integral of cosine squared and the integral of cosine to the fourth. The problem here is that this requires using the double angle identity that we have over here. I will show you which one. This one over here. But you need to use it for the cosine to the fourth. You basically need to use that identity on the other side squared over here. And this is not, very convenient. You can see it's going to open up. It's going to be a polynomial of integrals. It's just not fast, and convenient. So you can do it, obviously. It's just it's going to take you a little bit longer. So don't feel like you've done it wrong. It's just the longer way of doing this. The shorter way, well, take a look over here at what I have at my hands. I will erase again this work, but take a look at what I have in my hands. It's a product of sine and cosine to the same power. Why don't I factor that power outside? So I can have sine of x cos of x, and then have these squared. It's the same after all. Do I know anything about this product here? If you're keen, you might be able to cross-reference it with the sine cosine that is found in this identity. So I can suddenly replace that with sine 2x over 2 right now using that double angle formula. That's why it's so important to have these at the tip of your fingers, because now we can go back and we're going to dumb this problem down significantly by doing that replacement. We're going to get here sine 2x over 2 and all of it now squared. So if I go to the next step, I will pull the 1/4 to the outside, leaving me with sine squared of 2x dx. Now you might be thinking, I don't like this, how am I supposed to deal with it? Again, you can solve it using your knowledge of double angle formulae. Now again, what is this looking like? This is looking like the identity that we have over here. But the difference is that it's being squared. So you have this, essentially, with the substitution that x is 2x instead. What does that affect on the right-hand side? Literally nothing other than the argument over here. This is going to be having a substitution 2x. Wherever I see x, I replace it with 2x. So basically, this is just going to become 4x. And that's what I need to replace that sine squared of 2x with. It's literally that. So I'm going to copy it. And I'm going to bring it over here to show you again how I'm going to do it. This is what I'm replacing with in the next step. So I leave the 1/4 again untouched. I'm going to go ahead and take in here right now what? Well, 1/2 bracket 1 minus cosine of 4x right now, and then dx. That's it. So the 1/2 will be pulled all the way outside, and we will have a 1/8 now. And this breaks into two integrals, namely one of them is the integral of just dx right now, as you can see, and the other one here being the integral of cosine here to the 4x, just cosine of 4x dx. That is all. So you see again how simple it is once we understand what the substitution is that we need to make. It's just a home run from there. Now, to finish it off, again, this is a very simple integral. The integral of dx is simply, again, x. And the integral of this guy, he must have come from a sine 4x, but again, the 4 would have dropped outside if we took the derivative, so we want to actually divide this by 4, so we make sure again that this cancels. When we take the derivative of this, we immediately get this back. So as you can see, this is what we get for the result. Don't forget your integration constant and you're good to go. So very simple now that we know our patterns that we've established and a little bit on the identities at hand that I've provided you with. So again, in part 3, I'm just going to investigate some more integrals of similar form with a little bit more convoluted powers. But again, we're going to do one case of each: even, even, odd, odd, even, odd, and odd, even. Again, I hope that you found this video helpful. If you did so, again, please consider subscribing. Thanks again for watching.